Hello, Astronomy. Welcome to our third and final video lecture for Unit 2. So quick review. So in the first two videos for Unit 2, we took a pretty deep dive into some history. We went through Aristotle, to Ptolemy, Copernicus, Galileo, then to Brahe, Kepler, and Newton. And sort of the purpose of that sort of progression was to get us to the modern view of the layout of the solar system. Obviously, the heliocentric model that we finally settled upon. And in this picture, you can see the current layout of the solar system. So we're gonna go through this. Then we're gonna take a bit of a lesson into the age of the Earth. This video will probably be a short one. We can probably get it done in less than 15 minutes. So let's do it. So this picture, you can see the solar system. So you see the planets, you see the asteroid belt, you see the Kuiper belt. The relative distances of the planets to the sun are not at all accurate in this picture. The outer planets are way further out than this picture shows, but the relative sizes, they're also not perfect, but they're a good approximation. So let's go through these quickly. So the inner planets, you can see Mercury, Venus, Earth, and Mars. Again, the spacing here is inaccurate. These are small rocky terrestrial planets. Then we have the asteroid belt. Then we have the four gas giant outer planets, Jupiter, Saturn, Uranus, and Neptune. Then we have this belt called the Kuiper belt. So one thing that you should be able to do as a responsible student of science is name the planets in order. Hopefully you can already do that. I remember being in third grade and learning the planets in order, and we were told a mnemonic. And the mnemonic that I learned, this would be like 1987. More like 1988, maybe. Anyway, the one that we learned was Mary's violet eyes made John stay up nights, period. And of course, there was a period because back in the day, Pluto was considered a planet. So in Unit 4, when we get to Unit 4, we will go through all the planets and all of their glorious detail. We will discuss what happened to Pluto. We will discuss dwarf planets. But needless to say, in the early 2000s, around 2003, 4, 5, somewhere around there, Pluto was demoted to a dwarf planet. Now, the issue here, this Kuiper belt, notice there's this Kuiper belt and there's this asteroid belt. So the Kuiper belt is this belt of objects way, way out in the solar system, of which Pluto is a member. And this, starting in the late 90s and going into even now, we discovered more and more of these rocky objects in the Kuiper belt. Now we call them dwarf planets, and we'll discuss dwarf planets later. Pluto, I realize Eris. My face is covering Eris right now. But anyway, these are objects that have been discovered in the last couple of decades, and obviously we're not going to call them all planets, so we call most of them dwarf planets. I want you to think of Kuiper belt objects and asteroid belt objects as being objects from the formation of the solar system that did not form into planets. How planets form, we'll see in Unit 4. But basically, you have to have gravity that coalesces rocky particles together to get a planet. And the asteroid belt, in the reading, it mentioned this pattern of where planets should be, of the spacing, how like the outer planets are all twice as far from the sun as the previous one. Where the asteroid belt is should be a planet, if you look at the mathematical progression, but it's not. And the leading idea here is that Jupiter's gravity, Jupiter's pretty close to the asteroid belt, has a lot of gravity, sort of perturbed or tugged on the asteroid belt enough to where it couldn't get its act together to coalesce into a planet. So all this rocky debris would be the remnants of the origin of the solar system, and those remnants did not coalesce into a planet. Ceres is considered a dwarf planet because it's gravitationally round. And if Ceres was was near Pluto, we would call it a dwarf planet. So we do call it a dwarf planet. Okay, so Mercury, Venus, Earth, Mars, asteroid belt, Jupiter, Saturn, Uranus, Neptune, Kuiper belt. Okay, so now I want to do a quick little aside into the age of the Earth. So the leading number for the age of the Earth, the date for Earth's formation, was about 4.5 billion years ago. 4.5 billion years ago. And of course, there's lots of evidence for that. And I want to go through 3 or 4 bits of scientific evidence for that number. So the first, you can see this is just a picture of the Grand Canyon. You can see all these sediment layers. We have the ability to date these sediment layers using radiometric dating, which we'll talk about here in just a minute. But I start with this picture because the Earth, Earth looks really, really old. All right. No one can deny that Earth looks old. The sort of biblical idea of a 6,000-year-old Earth, there's really no evidence for that scientifically. And even if that were the case, it doesn't change the fact that Earth looks really, really old. So let's go through 3 bits of evidence for why the Earth is 4.5 billion years old. So the first is radioactive dating, and you've probably done this in physics class or some other chemistry class. And radioactive dating relies upon the fact that certain radioactive elements decay. Carbon-14 is probably the one you're most familiar with, and we're going to discuss carbon-14 in a minute. They decay from one element into another, and these elements have what's called a half-life, and you can look at this graph. A half-life is the time that it takes for half of the sample to decay into whatever it's going to turn into. I mean, you can see, so here I have where you have the rock as fully formed, or it's first formed. In every half-life, you have half as much of the radioactive isotope, right? Different elements have different half-lives. I put 3 here on the screen. Uranium-238, which decays into lead-206. So the parent isotopes are unstable. The daughter ones, in this case, are stable. So uranium-238 decays into lead-206. The half-life is 4,500 million years. That's a weird way to say it. Anyway, it's millions of years. Here you see carbon-14, half-life of close to 6,000 years. And so the range of dates for things that in the case of carbon-14 died, recently, within tens of thousands of years, you can use carbon-14. Uranium dating, potassium argon. This one, potassium argon, is a very famous one for dating when rock solidified from magma or lava. Its range is 0.05 to 4,600 million years ago. Again, that's an awkward way that's worded, but that's okay. So depending upon when something, in the case of carbon, died, or the case of like potassium argon, when the rock formed, you have a broad different range of isotopes, from half-lives in thousands of years to half-lives in the millions or billions of years. So for rocks, you might use potassium argon dating. For fossils, you might use carbon-14 dating. So carbon-14, let's talk about how this works really quick. So there's 3 isotopes of carbon, carbon-12, 13, and 14. Carbon-12 is the isotope that's most common. It's like 98, 99% or something of all carbon is carbon-12. It's very stable. You're mostly carbon-12. Carbon-14 is an isotope that is unstable, and carbon-14 is formed by UV radiation in the upper atmosphere. All right. So imagine carbon dioxide in the upper atmosphere where there's lots of UV. Some of that carbon gets turned into carbon-14, okay, due to ultraviolet radiation. Well, that carbon-14 will decay, right? And it takes about 6,000 years, 5730 is the actual number, for half of a sample to decay. So how does this relate to dating fossils? So right now you're breathing carbon dioxide, right? You inhale and you exhale carbon dioxide. A small percentage of the CO2 you're inhaling is based upon carbon-14. It's very, very, very small number, but you have some carbon-14. When you die, you stop inhaling carbon dioxide, right? So from the day of your death onward, the C14 is decaying. And so we can tell, because again, once you're a fossil or once you're dead, you don't take in more carbon dioxide. We can basically date how long ago a fossil died by how much C14 is left, right? And you can look at the half-lives. If 2 half-lives have passed, you're down to 25%. You can see how this diagram works yourself. So carbon-14 dating is good for dating when fossils died. And again, if it's a fossil from a million years ago, that's way too far away. That's way too far distant. C14 will not work. So maybe you have to use potassium argon dating for that. So that's one example of how we can date when, in the case of rocks, when rocks first solidified from magma into solid rock. And the oldest rocks on Earth, I want to say, date to about 4 billion years ago. Obviously, for a long period of time, when Earth was first formed, it was molten. And because potassium argon dating dates when rocks solidify, there's like a sort of a foggy window there at the beginning when we had to use other forms of dating. Okay, so in middle school, you probably did plate tectonics. So here we're going into my second evidence for an old Earth. You know, Earth is divided into major and minor plates. The average plate movement is about 1 centimeter a year. So the main thing I want to talk about with plate tectonics is the idea of Pangea, which you've heard of before. And I want to give an example of species of frog in Madagascar and India. So this shows a progression. You know, present day, here's Madagascar, here's India. They're very, very, very far apart, right? Just take a minute and look at this progression: 170 million years ago, 162, 135, 100, 88, and 60. And you can see where Madagascar was. Today, obviously, it's an island. Today, it's isolated. But you know, if you go back, say, 100 million years ago, Madagascar and India were connected, all right? And they separate around 88 million years ago and start moving apart towards 60 million years ago, which is about when the asteroid hit the dinosaurs. They're separate, and again today they're very far apart. You wouldn't have species, you know, swimming or flying from Madagascar to India. And the species we're going to talk about are two species of frog, and they're not swimming across the ocean from Madagascar to India. Okay, so again, look back at this diagram. 100 million years ago, they're connected. 88, they start to separate. 60, you get the idea. So if you had me for AP Bio, we've actually discussed this example before. So these two species of frog, and these are freshwater. They're not swimming in the ocean, all right? This one's native to Madagascar, this yellow one, and this sort of purple one's native to India and Southwest Asia. So in biology, we can use this technique called molecular clocks. And molecular clocks is sort of a tool to use to date when two species diverged. And you know, I'll make this brief. Basically, you use mutation rates of DNA. And if you know you have certain genes, cytochrome genes are common ones you use, because all life pretty much has cytochrome genes. Anyway, genes that mutate at a given rate. Say they accumulate one mutation every year, all right? If you know the mutation rate's more or less constant, you can take two species, see how many loci in their DNA have mutations. Like say these two species have 30 locations in their DNA where they're different. And if you know the rate, you can estimate when those two species diverged, right? And these two species of frog, which again are very isolated today, they're not going back and forth, they're not reproducing. One's Madagascar, one's India. Molecular clocks tells us that they originated from a common ancestor. You can look here, about 87, 88 million years ago. So they've accumulated enough mutations between the two species where it indicates that they were one species, or there was a common ancestor that of course could go from India to Madagascar 88 million years ago. All right, well, so that's great. That's biological evidence 88 million years ago. Well, look at the Pangea evidence, look at the geologic evidence. The date for Madagascar and India separating is also about 88 million years ago. So to me, this is a very, very, very powerful piece of evidence, because it's two completely different dating techniques. One is biological and one is geological. They have different origins, they have different methodologies. They're two totally different ways of dating things, but they're giving us the exact same number. All right, and that's, to me, that's, I mean, at that point, I'm convinced, because if two different people are telling you the same thing, two people who are not related, who don't have any of the same interests, it's probably the truth. All right. So my third bit of evidence is, of course, astrological. Did I just say that? Astronomical, and that's distances of things in space. So, you know, a light year is how far light goes in a year. A light year is a unit of distance, not of time. So you can look at this. The moon's 1.3 light seconds from the Earth. The sun's 8.3 light minutes. The nearest star, Alpha Centauri, to our sun is 4.4 light years. You can look at this globular cluster, and you can look at the Andromeda galaxy, 2.5 million light years away. So, you know, light travels 1 light year in a year. So when you're looking at the moon, that light was reflected from the moon, that the light's been traveling through space for 1.3 seconds to get to your eye, right? The sun, the light from the sun was given off 8.3 minutes ago, right? So if the sun blew up right now, we wouldn't see it for 8.3 minutes, right? So stars that are millions or more light years away, that light's been traveling through space to get to you. It's literally old light. You know, when you look up and look at the sun, which you don't look at the sun directly, but when you see the sun in the sky, that sun was given off 8 minutes ago. So that light's 8 minutes old. All right. So looking into space, looking into the sky is looking at ancient light. All right. When you're looking at the Hercules globular cluster, that light was given off 25,000 years ago, and it's been traveling through space for 25,000 years to get to your eye. So the Earth looks really old, right? Well, space looks even older, right? Space is ancient. Now, where these numbers come from, how we know, how far away Alpha Centauri is, we'll discuss in Unit 6, like where the numbers actually come from. But right now, just recognize that, again, light in space is old light. Okay, so we're going to end it there. I hope that was helpful, and I will see you guys next time.